Question 3. State 2 assumptions made about the motion of molecules in a gas and the derivation of kinetic theory of the gases. So there are a bunch of assumptions you can pick from. You just need to memorize them. 2, you could pick from a whole number. I'm going to say the motion of the particles is random. What does random motion means? That means no preferred direction and speeds vary over a range. That's what random motion means. And the second one I'm going to say is that the time between collisions is very small compared, very large compared with the time of collisions. So the time, I can't spell, it's appalling, my apologies. Time of a collision is very small compared with the time between collisions. So you could have said other things there. You could have said that they behave, all the collisions are elastic. You could have said that there are no intermolecular forces. There are large numbers of molecules, so the laws of statistics apply. There are a whole bunch of things that you can say there. You just need to learn them. Right, use kinetic theory of gases to explain why the pressure inside a football increases when the temperature of the air inside rises. Assume that the volume of the ball remains constant. So here we have the ball. Why is there a pressure inside the ball? Because gas molecules are smacking into the ball and bouncing off. When they do so, they have a change in momentum, which means that there must be a force on them. By Newton's third law, if there's a force on them as they reflect off, then there must be a force on the wall as well, an equal and opposite force. So as T rises, the average kinetic energy of the gas molecules also rises. So they've got more kinetic energy, which means they're going faster. This means each collision has a greater change in momentum. And that's Newton's second law, isn't it? So that's change in momentum, F is equal to delta mv divided by T. So each collision has a greater change in momentum, so a greater force is generated when it collides. But there's another reason as well. If they are moving faster, then they go backwards and forwards more quickly, so there are just more collisions as well. There are also more collisions. You think about this one hitting this wall, has to go all the way to this wall and all the way back again before it hits this wall again. It's going faster, does that in less time. So that's smaller, so a bigger force as well. So a bigger force is generated. I need to improve my handwriting. Okay. Right, assume that. Now it does say, explain why the pressure inside. Now I've actually only explained why the force inside increases, so I should really link this to pressure, because that's what the question asks for. And as area is fixed, then more force means more pressure, because P is equal to F divided by A. There we go. Right, so 3 marks. I think it's worth saying quite a bit there. I don't think that many lines is enough. I think you should write a little bit more. on a question like that for 3 marks. Okay, so this is a big gas laws question, big 6 marker here. But I think actually it's relatively easy. So the laws of football require the ball to have a circumference between that much and that many millimeters. The pressure of the air in the ball is required to be between that much above atmospheric pressure. The ball is inflated when the atmospheric pressure is that much and the temperature is 17 degrees. So 17 degrees Celsius is 17 plus 273, it's 290 Kelvin. The mass of air is that much inside the ball and the circumference of the ball is that much. Assume that the air behaves as an ideal gas and that the thickness of the material used is negligible. Deduce if the inflated ball satisfies the laws of football about pressure. Right, okay. So it doesn't matter about this circumference thing here. We're just interested if the pressure ends up being this much above atmospheric pressure. Right. So, first of all, it will be useful to work out how many moles of this substance there are of the air inside. So the number of moles of something is equal to its mass divided by its relative atomic mass or relative molecular mass. Now, this is a bizarre one because it's done in grams. So just make sure that that unit there and that unit there match. So the mass is 11.4 and divided by 29. So 11.4 divided by 29 and we get 0.39310 ... and that's moles of air. Okay, so we now know how many moles of air there are inside the ball. We're also going to need to know the volume of the ball. So the volume of a ball is given on your formula sheet. Volume of a sphere is equal to 4 over 3 pi times by r cubed. But we don't even know what the radius is. We actually know what the circumference is. So the circumference of the ball here, that's 0.690 meters. So the circumference of a ball is equal to 2 pi times by the radius. So the radius is equal to the circumference divided by 2 pi, which is 0.690 divided by 2 pi. Right, we're going to need that later, so I'm going to store that in A. So I've stored that in A. Okay, here is the radius. So we want 0.69 divided by 2 pi gives us a radius of 0.1098 meters. So we can now continue our volume calculation by substituting that into r squared. So we've got 4 over 3 times by pi times by 0.1098 ... and that's all got to be cubed. So we want to raise that to the power of 3. Then we got that, times it by pi, and we got that, times it by 4, and divide it by 3. And we get the volume is equal to 5.547 times 10 to the minus 3 meters cubed. And it is in meters cubed because I changed that to meters. Much easier to do that right at the beginning than to worry about what on earth is going on with millimeters cubed here. Okay. Right. Now we need to work out the pressure. So we need the ideal gas law. So pressure is equal, PV is equal to nRT. That's the ideal gas law. We want pressure, so P is equal to N times by R times by T. divided by V. Okay. Well, we know all of these now. That one is that, that's on the formula sheet, that is that, and V is what we just worked out there. So, we want to do the number of moles of air, which was my memory A, divided by my volume, which was that. Then I want to times by the gas constant R, which is here, 8.31, times by the temperature. We want the moles of air, and we want to divide the whole thing by the volume. Okay, so far I've done that bit, so I need to times it by 8.31 to get that bit, and then I need to times by 290 the temperature. And I have now, that's 1.707 times 10 to the 5 Pascal. Right. Next step then. This doesn't lie in this range, so what's going on? Well, this is the pressure inside the ball, but the pressure there's a pressure outside the ball as well. There's atmospheric pressure outside the ball as particles hit the outside. And what you're interested in is how much more pressure there is inside the ball than outside the ball. So we need to take away atmospheric pressure, which is there. So the change in pressure is equal to the pressure inside take away the pressure of the atmosphere. So that's going to be equal to 1.707 times 10 to the 5, take away 1.00 times 10 to the 5, so let's take away 100 of 1,000, and we get 70,000 770 Pascal. So the final thing is deduce if the inflated ball satisfies the laws of football about pressure. Well, that number lies between that value and that value, so yes, it does pass the test for the laws of football. And that is question 3.